I'm going to go through a fairly straightforward problem that I found on Math Exchange, posted back like in 2015. And we're given that A, B, and C are real numbers such that this condition or this constraint holds the AB plus BC plus AC is equal to 12. So we're given that as a constraint or an initial condition, and we're supposed to maximize the product ABC. Now, it turns out this is, again, there's not too many steps here because it's just an immediate application of what they call the arithmetic mean geometric mean result. Now, I'll just write that down. In the general case, there's the two variable case that everybody's familiar with, I think, but let's say that we have X plus Y plus Z. Okay, and we're interested in its arithmetic mean. This is sometimes just abbreviated AM, arithmetic mean. Okay, so this is what the AM of the AM-GM inequality. All right, so that's arithmetic mean, AM. That's going to be greater than or equal to. And there's an interesting geometric proof of this involving squares and rectangles. But what you do is now we're going from the operation of addition to multiplication. And instead of dividing by 3, we're extracting the third root of the product X, Y, Z. Okay. And this is really one of the most fundamental inequalities you could ever get, because here you have the operation of addition and division. Over here you have the operation of multiplication. Okay, and you're extracting the third root, which is a multiplicative sort of concept. All right, so you can actually use this, I think, to prove the special cases of Cauchy-Schwarz, and so and back and forth, I think. But this is called this is the GM side of the result right here, and this stands for geometric mean. Okay, stands for geometric mean. Okay, now you can see that solving the problem now is pretty straightforward. We're just using AB to be like the X here, BC to be like the Y, and AC to be like the Z. See, this says X, Y, and Z, but X, Y, and Z can be absolutely any type of algebraic expression that you want. So, you know, it expands out to very large expressions. And again, you can see here you have X, Y, and Z juxtaposed. And so you have AB times BC times AC, all cube rooted. Now, probably this perhaps is the biggest step right here. See, since we are trying to maximize ABC up here, all right, it makes sense to get these together by the properties of exponents. You see, you have two copies of A. Here's an A, here's an A, here's a B, here's a B, here's a C, here's a C. And so you can write that, and this works because of the commutative property of multiplication. So you have A squared, B squared, C squared, cubed root. Now we get to actually use our given. AB plus BC plus AC, it actually sums up to 4, or 12, excuse me. This piece right here sums up to 12, and that's just given, right? It's given. So that's what I'm doing down here. 12 over 3 is certainly 4. You still have the greater than or equal to, but now it's greater than or equal to the cube root of the quantity A squared, B squared, C squared. Now, what did we do at this step right here? We just cubed both sides. You see, cubing and cube rooting are inverse operations. So we cubed this, and we also cubed this entity right here. All right, but that has the effect of just making the operator evaporate, right? And so now at this step, we have 64 is greater than or equal to A squared, B squared, C squared. We're not interested in that. We're interested in maximizing ABC. And so we square root both sides. Properties of exponents give us that 8 is the maximum value of the product. Now, it's pretty easy to see that would happen at 2, 2, and 2. But I used to wonder what would happen if you had like 1.99, let's say, times 2. You know what I mean? I used to kind of wonder about those cases, but because of the AM, maybe 2.01, you know, and then maybe 1.99 maybe. It seemed like that might be close, but it turns out the 2's always win. So again, this was just something I used to wonder about until I became familiar with the AM-GM inequality. All right, y'all, let me know what you think.